This video is a review of linear momentum, impulse, Newton's law, especially Newton's second law, and calculus. This is not an introductory video on any of these subjects. Matter of fact, it's very much a review video on these. And the reason I'm trying to lump them all together is most students, when they take math and calculus and physics, they start out and you learn it kind of simple, and you probably learn physics in a non-calculus based way, and it's a very difficult way to understand that. And then when you learn concepts like linear momentum and Newton's second law, you learn them probably months apart from each other, and the interaction, and it kind of lets you confused. And so as a review, I kind of want to step back and kind of see what the big picture is. So if you see the big picture, then the story seems much more simple, especially when you use calculus. And we're going to start with the most general form of Newton's second law. Probably when you learn in physics the first time, you learn Newton's second law, and you probably still may remember it. You learn something like F equals ma, and that what you're taught was Newton's second law. Well, that's truly not what Newton said. That's a very special case of how you can get from Newton's second law, but Newton really said this is the most general form, and that's the way you really want to understand things. And you understand things in the most general form, and then you understand what assumptions you have, and then when you solve a problem, at least you know that you're making the proper assumptions for the formula equation you're using to solve it. And so this is, in this blue circle, is the Newton really said for this second law. He said the sum of all the external forces acting on selected objects at an instant of time. Now, we need to think, when you solve any problem, the first step you want to say is, what am I trying to solve for? And you want to have your system contain the elements in that. For example, let's say I'm going to solve for the velocity of me on my bike descending down a hill. And so you can think, what objects should I select for my free body diagram? Should it be just me or just the bike? You say, well, I'm thinking we're kind of objects going together. We're a system, the me and the bike. So you could probably say the system is both me and the bike. If you said the system was, because we're thinking that system going together is kind of has the same kind of velocity. And if you just had me as the system, then you'd have to worry about things like the forces between me and the bike and the pedal. And so you want to try to have your system chosen to be the system that gives you the answer that you want to solve for and don't include internal forces that you don't necessarily need. Because you can see that one of the key words here is external force. So think of your system, and what forces would you want to have, and then don't worry about internal forces. The Newton's second law says only then consider forces from the outside of that system acting on that system. And so that system could be a singular object like this marker, or it could be two objects like this, or it could be me holding these markers, or me and the earth. But once you've chosen, so that's the key, is you always say, write down, this is my system, and you draw it, and that's called a free body diagram typically, and then only worry about the forces acting externally from the universe acting on that system. And so Newton was saying, now he's saying, add up all those external forces and add them up at an instant of time. And these forces are going to be vectorial. They can be from many different directions. And you can think they're either the sum or the net, the same thing. And he's saying, so now I've chosen my system, and I look at all the forces acting on it from external, from not including internal forces, and all that equals the rate of change of linear momentum as a function of time. And that's what Newton's second law really says. And you can see this is a vector quantity for both momentum and a forces quantity. And now thinking about assumptions, the only assumption that we have to make to say I can use this equation is that the frame of reference is inertial or non-accelerating. And why do I have to say that? So I think we'll talk about later, but momentum is related to velocity. And you always have to say velocity relative to what? And this is saying I have to have velocity relative to an inertial non-accelerating reference frame. For example, let's say I'm a passenger in a car and I'm reading a book in front of me, and the driver accelerates from red light and goes forward, and I'm holding this book at a constant distance in front of me. To me, from my frame of reference, if I become the frame of reference, to me that book looks like it's not moving forward or backwards; it's staying in the same place. However, I'm not a non-inertial reference frame. I'm accelerating, so it's not. Therefore, this equation is not valid. So what really is an inertial reference frame? Well, really, on Earth, there really is truly no such thing, because you can think the Earth, on the surface of the Earth, the Earth is rotating around 24. It takes 24 hours for it to spin, and anything that's and if I put a coordinate system on the surface of the Earth, well, that coordinate system is moving around, and so therefore there's acceleration towards the center. So that's not one, but is that practically, sometimes when you're solving a problem, you say it doesn't really matter. This acceleration, I'm still turning quite slowly. It takes 24 hours for me to spin around, and so my acceleration due to that is in the order of 0.3% of the gravitational force acceleration that I see. So it's very, a lot of times the assumptions say, well, I'll ignore that. I'll say the surface of the Earth is an inertial reference frame, and that's pretty, usually that's a very practical way of doing it, and doesn't introduce hardly any error at all. In addition, you can think, the Earth is revolving around the sun, and the universe is accelerating away from each other. But in general, for most real-world problems you're going to solve, the surface of the Earth is a acceptable frame of reference. But you should be aware that you at least made an assumption, and it's not 100% true. But for most cases, it's relatively true. And so that's the only assumption that goes with that. And that makes this a very powerful equation to solve kinematics problems involving force and motion. That the sum of the external forces acting on my selected objects at an instant time is equal to the rate of change of linear momentum versus time. And so now, kind of, what's linear momentum? The true value of linear momentum has to consider relativistic terms. So, because your speed may be very, very high, and so what the relativistic linear momentum is, we give momentum typically give it the letter p, and it's a vector, and it equals the rest mass times the velocity is a vector, and then it's multiplied by 1 over the square root of 1 minus the speed squared minus the speed of light squared, and that's called the Lorentz factor. Now, for most real-world problems, anything that any human has ever made, the speed of this object is fractionally tiny relative to the speed of light, and so this ratio is very close to 0, and 1 minus 0 is 1. Square root of 1 is 1. So this term, essentially, for any practical human endeavor or activity or anything we're going to analyze, this is pretty much 1. So therefore, we generally make the assumption that this is close enough to 1. So therefore, when we solve it, we just say momentum equals the mass times the velocity. And no, this is not speed, because both are vectorial functions. And so momentum, like any vector, has both magnitude and direction. And obviously, the magnitude at the smallest could be 0. But to solve some problems, sometimes you want to, if you just worried about motion in this direction, you may not have to worry about the good things. You don't have to worry about the forces that are in 90 degrees from that, so up and down or in and out of the board. So sometimes it's easy to just break it up and say, so you can say in the x direction, if you call this, that momentum in the x direction is the mass times the velocity in the x direction, and same likewise for the other directions. But when you do that, again, you have to pick a coordinate system. So let's say my coordinate system is like this, and we'll call this the positive x in this direction, and let's say this object here, let's say this is my coordinate system here, and this object's going this way, so it's going in the negative x direction. In that case, you would say the momentum relative to this coordinate system would have a negative term as far as momentum. Now let's go to a special case of Newton's second law, which you probably learn as Newton's second law, and you can see how it's just a special case of this general case. And so we'll start with the general case that the sum of all external forces acting on an object at an instant of time equals the rate of change of linear momentum as a function of time. We're going to substitute in our value for limited momentum, which is mass times velocity. And now we're going to make our third assumption. So this assumption now is going to hold true for this new form, is when we'll make the assumption mass is constant, and since mass is not changing as a function of time, I can bring it out. And then so mass times the rate of change of velocity with respect to time, and we define rate of change of velocity with respect to time as acceleration. Again, that's a vector, and now this is our very special case of Newton's second law, but we have to make the assumption that mass is constant. And if mass is not constant, actually this is a quite more complex equation that you have to end up, because you have to worry about, because your system now has mass changing, for example, a rocket and fuel's leaving it, and if you have your system being the rocket not including the fuel leaving it as exhaust, then you have to worry about, then you have to consider that the relative velocity of the fuel leaving the rocket relative to the velocity of the rocket. So it's a very complex thing I'm not going to go into in this video, because in most cases we're going to be solving problems where the mass is constant. So now you can see that this is just a special case. Sum of forces external to an object acting in time equals mass times acceleration of this. And it had this additional assumption that mass is constant. Now going back, so this is very helpful for solving problems, especially if the external force is over time is a constant value. For example, if I'm going to, let's say my system is this marker, and I'm going to say I'm going to drop it, and I'm interested in its motion and its velocity as it drops. Well, the force acting on it will ignore wind, frictions, and things like that for this example. So the force acting on, if you do a free body diagram, the force acting on is the gravitational force, and as it drops from this height to this height, that force is quite constant. I mean, because we're relative to the distance to center of Earth, it's not that much different, and the mass is staying constant. So therefore, it's a good way to solve that, and so therefore, this would be a good way to understand how the acceleration of that part just happened right there. But you realize that you can also do it. You can find the velocity using this methodology, the change in velocity over time. So now, let's say we had a case where the force wasn't constant over time, and we really kind of understand what's happening to the linear momentum of my system. And so we're going to start with this general form again, and what we're going to do is we're going to multiply both sides, this force side and this side, by dt. So dt over dt is 1, and it ends up, so I now have this kind of form. Okay, so the sum of external forces factorially dt equals dp. And I'm now going to substitute in my value for linear momentum is mass times velocity. Again, I'll make my assumption the mass is constant, so I can bring it out of the derivative. So now I have mass times dv. And now I'm going to make this is valid, this next part's going to be valid for multiple masses, but we'll just kind of simplify and consider one mass, to make, just so we don't have to add multiple values together here. So we're going to take this form of the equation now and just take the integral of it. Okay, so I'm going to integrate on this side, and I'm going to integrate this side. In that integral, so the integral of the sum of all the external forces dt has a special word in physics called an impulse. And you can see that's vectorial as well. And impulse in English, we typically think impulse is just happens at a moment of time that's it's so small it's almost insignificant. In this, an impulse in a physical world is just for some duration that force is acting. So it can be just from an initial time to a final time. So this is an impulse, and now if we take the definite integral, because let's say I have a problem, I'm thinking I know its velocity at some initial time. I want to know its velocity at or either velocity or momentum at a final time. So I'm going to take this integral, and I'm going to integrate from an initial time to a final time. Okay, so I'll take all the forces, sum all the forces acting on my selected object, and take the integral with respect to time, from initial time to final time, and that equals, with assuming I have a constant mass here, so that's the mass times the integral of the velocity, so from some initial velocity to this final velocity. And so if I do this, so I take that integral, so that's just my mass times my final velocity, my mass times my initial velocity. Well, this term, mass times final velocity, is just my final momentum, linear momentum, and this term is just my initial linear momentum. So that's my change in my linear momentum. So this external impulse from external forces causes a change in the internal linear momentum of the system. Now, viewing that graphically, so I had a case where I have some force that's varying as a function of time acting in my system, and so that's kind of this red line. I just kind of drew that from t initial to t final, and sometimes it was pushing it this way, and sometimes it was pushing this way, and the integral, or the area under this force curve, external force or as a function of time, that integral, that area, that value here, that is my impulse. That's the area under this curve. That's what that value says. So if I can measure all the force that I have vectorially and integrate it, then I know that external force causes a change in the internal momentum of my system. So that's the way to solve for problems when I have a changing force. So I can understand how the linear momentum and therefore the velocity vectorially changes over time. Now, we talked about systems before. We think about now, sometimes you want to draw your system so that you don't have, that you can include all things so that there's no external forces acting on it at all. So, for example, a case here might be, it's very hypothetical. Let's say I'm in space. I'm in deep space, and I'm so far away from any planets and any stars that there's essentially no gravitational force acting on me, and I have this marker in my hand. And I'm gonna have this system be me and the marker, and we're just floating in space, and there's essentially no external forces acting on us. And so that really makes this equation quite simple, because sum of all external forces acting at that instant time is zero. So 0 equals something always makes it really easy. And this further makes assumption that there's I don't exchange, that my marker and I don't exchange any matter with the rest of the universe. So the system will always consider me and the marker. We're the system, and therefore there's no change in mass over time. And that's a really convenient one, because now this equation becomes quite simple, and we call that a closed system. And so now think of me and the marker floating in deep space, and I throw that marker to the right. What happens to me? So the system is me and the marker. This total mass is stayed the same. So the marker is now gone. And if we were saying that, so there's this the external force has been zero all the time. There's no impulse acting on us. Therefore, this zero, my rate of change of linear momentum versus time is zero, which means therefore it's a constant. There's no changing linear momentum. So therefore, at the moment that marker left my hand, if we could measure its velocity relative to an inertial reference frame, then my velocity is going to be the opposite way, and it's going to be inversely related to my mass relative to the mass of the marker. Now, the inconvenience to do that, so that system, clearly when I was throwing that marker, as I'm moving it, I was putting a force on it, and it was by Newton's second law, I was putting an equal and opposite reaction force on me. So if the system was just me, then I would have had this external force of the marker, and so that would have made it much more complex, because I would have to worry about this complex force between me and the marker. But since I drew the system including both me and the marker, it became now an internal force, not an external force, and so I didn't have to worry about it. And so the moment that marker left my hand, I can do the calculation of what it's. If I knew its velocity, I would also then know my velocity, simply from using this equation. So now we have a question for you, kind of a wrap-up question, two questions actually. So what happens to the sum of the linear momentum of a system? So I'm going to sum up so each mass has some velocity, and so we can sum them all up in my system if the sum of the external forces acting in the system equals 0. Think about it. Okay, so sum of all external forces equals 0. What happens to the sum of the linear momentum of the system? Well, it's kind of like my example of me in outer space. I mean, so the sum of forces equals 0. So the rate of change of linear momentum of time it'd be also 0. Therefore, the initial and the final linear momentum is the same. It's the same at all times, even in between, and therefore it doesn't change. And for a two-mass system, the final linear momentum of the system equals initial linear mass of the system when the sum of the external forces acting on this entire system is 0. And so therefore, if I'm mass 1 and the marker's mass 2, my mass times it's my initial velocity plus the marker's mass times this initial velocity, that's the initial linear momentum of the system, equals the final linear momentum of the system, which is my mass times my final velocity plus the marker's mass times its final velocity. And this is known as conservation of linear momentum, and it only holds true if the sum of the external forces acting on the system is 0. A typical case where we use linear momentum is, for example, when two cue balls come together, and you think about just the moment right before they touch, and then they have potentially really big interactional forces. But if you have your system be both of the cue balls rolling essentially, and you're just worried about the horizontal motion, so you're ignoring since things are vectorial, you can ignore the gravitational forces on it, and since it's rolling, there's probably almost no friction, and so you think about if your system is both of the pool balls, and they have some huge internal forces interacting, but from the moment they just first touch, the moment they first leave, the external forces acting on them in the horizontal axis is quite small because the friction is almost close to 0 because they're rolling, and therefore you can use an equation like that to solve for what their initial final velocities are given their initial velocities. And so therefore, you always have to know what assumptions you're making, but sometimes you use equations saying that, that's a pretty good assumption. Now, if the problem had been, for example, me standing on Earth with my feet on the ground, I'm going to throw this marker, and this marker goes off to the side. I don't go shooting off with some velocity to the other side, and so you think about why don't I have this velocity to the other side? What's different? Well, if the system is me and the marker, there's a big change on Earth. Is I'm standing on the Earth, so there's an external force acting on me. It's me standing on the Earth, and so if I go this way, if I throw the marker this way, there's forces between me and the ground that keep me from having this velocity. So therefore, you always have to, the concept of external forces, when you think about it, you draw your system, you got to think of every external force that can possibly act on it. So now another question, what if the sum of external forces is not equal to 0? So I have a system, and the sum of external forces is not equal to 0? Well, what does that say? Well, that says the sum of the linear momentum is going to change as a function of time. So my linear momentum of my system changes versus time.